In this video, we're going to take three vectors, v1, v2, and v3 that are in R3, and we're going to ask whether or not the set that they form is a linearly independent set or a linearly dependent set. So here are my three vectors. v1 is 1 minus 2, 0, v2 is 0, 2, 1, and v3 is 2 minus 6 minus 1. Is the set formed of these three vectors linearly independent? What we first really need to do here is rephrase this in terms of the definition of linear independence. The definition requires us to consider a linear combination of the three vectors obtaining 0 and ask whether or not that homogeneous equation has non-trivial solutions. So does the homogeneous equation have non-trivial solutions? If it does have non-trivial solutions, that means there are interesting relationships among these three vectors, and they are linearly dependent. If it has no non-trivial solutions, it means you can only put 0, 0, and 0 in front to get 0, and they are linearly independent. There's no interesting relationships among them. It's probably a little bit more convenient at this point for us to rephrase this in terms of matrices. So I'm going to let A be the matrix whose columns are our three vectors, v1, v2, and v3. And the question now becomes, does the homogeneous matrix equation A times x, which is just shorthand for the linear combination of those vectors, have non-trivial solutions? In order to answer that, we look at the augmented matrix. I'll put a column of zeros next to it, and we'll row reduce this matrix and see whether or not there are non-trivial solutions. So the first thing I'm going to do is eliminate the minus 2 here, using what's going to be a pivot position here, this 1. So I'm going to take twice row 1 and add it to row 2 and replace row 2 with the result. And when I do that, I'm going to get 0 in the first position, and then 2, minus 2, and 0 in the remaining positions. I'm then going to scale row 2 here by a factor of 1/2, so I'll have 1s. And then you can see that the resulting row 1 minus 1, 0 is the same as the third row, so if I replace the third row with itself and I subtract away the second row, I'm going to get a row of zeros. We're in the reduced row echelon form at this point, and the important thing is locating where these pivot positions are. I see a pivot here, I see a pivot here, but what's important for us now is that in this third column there is not a pivot, so there's no pivot in that third column, which means when I write down the solutions to this homogeneous equation, yes, it's consistent, it was always going to be consistent, it has a trivial solution, but more than that, the solutions will have a free variable in it, and therefore there are non-trivial solutions to that homogeneous equation. So here's our conclusion. Ax equal to 0 has non-trivial solutions. Therefore, according to the definition, the set containing my three vectors that are the columns of this matrix A is linearly dependent. Let's take this a little further now. We've answered our initial question, is it dependent or independent? Yes or no. We've answered that kind of binary question, but we're going to dig a little bit deeper by looking at the solutions to the homogeneous equation. So the solutions to Ax equal to 0 can be described by reading off them from the reduced row echelon form. x1 is minus 2x3, x2 is equal to x3, and x3 is the free variable, and that's why we have these non-trivial solutions, because of that non-pivot column, because of the free variable. If you prefer, you can write this in vector parametric form. X is the vector whose entries are our three variables, x1, x2, and x3, and we can replace them with the result above, and typically we factor out the parameter x3 just to emphasize that the solutions to the homogeneous equation are minus 2, 1, 1, and scaled by our parameter x3, our free variable. So what does that tell us about linear independence and dependence? Well, it tells us the weights of our homogeneous equation, of our vector equation. It tells us which linear combinations give us 0. So if I take x1 and I replace it with minus 2x3, and I take x2 and I replace it with x3 per my solutions, and I take x3 and whatever I choose it to be, I put that as a weight for v3, I am guaranteed to get 0 as a result. So what we're seeing here are all the possible ways of rewriting our solutions here, all the possible ways of taking linear combinations of our three vectors and getting 0. We're seeing these dependencies among these three vectors. For instance, if I take x3 to be equal to 1, I get one example of a linear combination of my three vectors that give me 0. -2, 1, and 1. And you can see here, potentially you could solve for any one of these three vectors and express it in terms of the other two. They are dependent on each other. Nothing special about the value I took for x3. I could take x3 to be -1/2, and if I did that, I'd have a 1 in front, and -1/2, and -1/2 for the other weights. They don't have to be rational numbers or integers. They could be any real number. I could take x3 to be pi if I wanted to, and -2 pi, pi, and pi would be weights that would give me a linear combination that would result in 0. All three of these equations here, these three equations right here, are what we call linear dependence relations. And in fact, they're non-trivial ones because I'm not just putting 0 in front of my three vectors. So these three equations I've written here, or this one above, this very general one, are examples of non-trivial linear dependence relationships. They show the ways that my three dependent vectors are related to each other. So make sure you kind of divide this into two parts. The first part is it linearly dependent or independent? And that has to do with whether or not there are non-trivial solutions or not. That is a yes or no question. But in the case that there are non-trivial solutions, you can actually look at those solutions and describe the non-trivial linear dependence relations among the three vectors.